29,000 feet above Berlin, Squadron Leader James Peterson's oxygen mask froze solid as his Spitfire Mark 14 screamed past a Messerschmitt 109 that simply couldn't climb any higher. The German pilot's eyes widened in disbelief as the British fighter, which had been gasping for air at this altitude, accelerated away with impossible power. What the Luftwaffe didn't know was that deep in a secret Derby factory, Rolls-Royce engineers had just broken every law of engine design they'd been taught. By combining a two-stage supercharger with intercooling technology stolen from American bombers and a radical fuel injection system, they created a monster. The Merlin 66 engine producing 2,050 horsepower at altitudes where German engines could barely breathe. This is a story of how British engineers turned a failing engine program into the most powerful inline aircraft engine of the war. If engineering triumphs and the untold stories of aerial supremacy fascinate you, consider subscribing as we uncover more revolutionary moments that changed the course of history. March 1943, and the Rolls-Royce facility at Derby was in crisis. The standard Merlin engine, which had powered Britain to battle Britain, was being outclassed by newer German engines above 25,000 feet. Chief Engineer Stanley Hooker stared at test results, showing German fighters consistently achieving superior performance at high altitude. The Americans were threatening to switch entirely to their own engines, and the Soviet Union was reporting that Spitfires couldn't protect high-altitude bombing missions. Britain's aerial superiority was evaporating into thin air, the stratosphere. The breakthrough came from an unlikely source. Hooker had been studying captured German turbocharger designs and American intercooler technology when he realized everyone was approaching the problem wrong. Instead of trying to make one perfect supercharger, why not use two imperfect ones in series? The first stage would compress air moderately, cool it down, then feed it to a second stage for final compression. It was mechanically complex, theoretically risky, and absolutely brilliant. The team faced immediate skepticism from Rolls-Royce management. Adding a second supercharger stage would increase weight, complexity, and cooling requirements. The intercooler alone would add 50 pounds to an engine where every ounce mattered. But Hooker had done the mathematics. The power gain at altitude would more than compensate for the weight penalty. More importantly, it would give British fighters a performance envelope that German engines simply couldn't match. The first prototype exploded on the test stand, sending shrapnel through the factory roof. The second caught fire. The third vibrated so violently that it walked off its mounting bolts. Each failure taught them something crucial about the extreme pressures and temperatures they were dealing with. The intercooler needed redesigning to handle air compressed to nearly 4 times atmospheric pressure. The supercharger gears required new metallurgy to survive the enormous loads. Every component had to be re-engineered for conditions that no aircraft engine had previously encountered. Working conditions were brutal. The Derby factory was under periodic Luftwaffe bombing raids, forcing engineers to continue calculations in air raid shelters. Materials were scarce, with every ounce of aluminum and high-grade steel being rationed. They were competing with tank production, shipbuilding, and ammunition manufacturing for resources. Yet Hooker's team pressed on, driven by reports from the front showing British pilots dying, because they couldn't fight effectively above 25,000 feet. The breakthrough came from an American B-17 bomber that crash-landed near Derby. Hooker's team salvaged its intercooler system and discovered the Americans were using a different cooling principle that was more efficient than British designs. Within days, they had adapted it for Merlin, creating a compact intercooler that could cool compressed air by over 100 degrees Celsius between supercharger stages. This cooling was crucial, as it increased air density and prevented detonation in the cylinders. By September 1943, they had a working prototype producing 1,650 horsepower at 30,000 feet, where the standard Merlin produced barely 1,000. But Hooker wasn't satisfied. He knew German engineers were working on their own high-altitude engines. Intelligence reports suggested the Luftwaffe was developing the Ta-152 fighter specifically for high-altitude combat. Britain needed not just parity, but decisive superiority. The solution came from studying American fuel injection technology, combined with British innovations in combustion chamber design. By precisely controlling fuel mixture at different altitudes and incorporating sodium-cooled exhaust valves, they pushed the engine beyond 2,000 horsepower. The Merlin 66, as it was designated, could maintain combat power at altitudes where German engines were struggling to maintain cruise settings. Test pilot Jeffrey Quill took the first Spitfire Mark 14 equipped with a new engine to 43,000 feet, a height previously achieved only by specialized reconnaissance aircraft. His report was euphoric. The aircraft climbed like a rocket, accelerated at altitudes where previous Spitfires wallowed, and maintained control responsiveness in air so thin that German fighters stalled and spun. The engine, note, he reported, was different too, a distinctive howl created by the two-stage Supercharger that would soon terrorize Luftwaffe pilots. The first combat test came in November 1943, when Squadron 610 intercepted a high-altitude reconnaissance Junkers 86 over Scotland. These aircraft typically operated above 40,000 feet, untouchable by conventional fighters. Flight Lieutenant Terry Spencer pushed his Spitfire 14 into a climb that would have been suicidal in earlier marks. At 38,000 feet, where his old Spitfire would have been wallowing like a dying fish, the Mark 14 was still climbing strongly. He caught the Junkers at 41,000 feet, the German crews shock evident as they desperately tried to climb higher. The reconnaissance aircraft that had photographed Britain with impunity for months was shot down in flames. Back at Derby, Hooker's team was pushing even harder. They had achieved 2,050 horsepower, but reliability was marginal. Engines were lasting barely 50 hours before major components failed. The two-stage Supercharger generated temperatures that warped cylinder heads and pressures that cracked engine blocks. They needed better materials, but wartime Britain had none to spare. The solution came from an unexpected source: melted-down church bells. The bronze contained trace elements that, when added to aluminum alloys, significantly improved high-temperature strength. The production engineering challenge was equally daunting. Manufacturing tolerances that were acceptable for standard Merlins caused catastrophic failures in the high-pressure Merlin 66. Rolls-Royce had to retrain their entire workforce, implementing quality control procedures borrowed from Swiss watch manufacturing. Components were hand-selected and matched in sets. Each engine was essentially hand-built, with skilled craftsmen spending weeks on individual units. It was the antithesis of mass production, but it was the only way to achieve the required reliability. Intelligence reports from Germany revealed they were aware of the new engine, but didn't believe the performance figures. Captured Luftwaffe documents dismissed claims of 2,000-plus horsepower as British propaganda. German engineers insisted it was thermodynamically impossible to extract that much power from a 27-liter engine without it destroying itself. They were technically correct. The engine should have destroyed itself. But Hooker's team had found ways to manage the destruction, replacing components just before they failed, operating at the very edge of material science. The impact on pilot morale was immediate and profound. Squadron leader James Johnstone, who had been shot down twice by high-flying German fighters, described his first flight in a Merlin 66-powered Spitfire as redemption. The aircraft climbed to 35,000 feet in under 15 minutes, a feat that took German fighters nearly 25 minutes if they could achieve it at all. At that altitude, while German pilots struggled with oxygen deprivation and engines surging, the Spitfire retained enough power for aggressive maneuvering. The Americans took notice. General Jimmy Doolittle, commanding the 8th Air Force, witnessed a demonstration where a Spitfire 14 climbed from ground level to intercept a 17 formation at 28,000 feet, conducted a mock attack, then climbed another 10,000 feet, all within 20 minutes. He immediately requested 100 aircraft for bomber escort duties. The same Americans who had been threatening to abandon British engines were now desperately requesting them. Production remained agonizingly slow. Each Merlin 66 required approximately 3,000 man-hours to build, compared to 800 for a standard Merlin. The Supercharger gears alone took a week to manufacture and balance. Rolls-Royce was producing perhaps 20 engines per week when the RAF needed hundreds. Lord Beaverbrook, Minister of Aircraft Production, threatened to nationalize the Derby factory if production didn't increase, now understanding that the limitation was physics, not politics. The engine's complexity created maintenance nightmares in the field. Ground crews accustomed to basic Merlin maintenance found themselves dealing with intercooler systems that required precise adjustment, boost pressures that could destroy an engine if set incorrectly, and temperatures that required new types of lubricants. Special training programs were established, but many squadrons initially had more aircraft than qualified mechanics to maintain them. Combat reports from early 1944 revealed the engine's true impact. Over France, Spitfire XIVs were bouncing German fighters from above, something previously only possible for Germans. Luftwaffe pilots reported being unable to escape by climbing, their traditional defensive tactic. The psychological effect was profound. German fighters that had operated with impunity at high altitude were now the hunted. Several experienced German aces were shot down simply because they couldn't believe a Spitfire could reach them at 35,000 feet. The engine's success created unexpected problems. Pilots had to be retrained for high-altitude physiology. The human body wasn't designed for combat at 40,000 feet, even with oxygen. Several pilots lost consciousness from the rapid pressure changes during combat maneuvers. New pressure suits were required, adapted from experimental designs intended for stratospheric research. The aircraft was exceeding human limitations, a problem nobody had anticipated. Technical challenges continued to emerge. At extreme altitude, fuel vaporized before reaching the cylinders, causing power loss. The solution required heated fuel lines and modified carburetors that maintained fuel pressure at near-vacuum conditions. Spark plugs failed from extreme temperature cycling. Propellers needed new blade designs to bite into air barely denser than sea-level conditions on Mars. Every component had to be redesigned for an environment that was essentially space-like. The true test came during Operation Argument in February 1944, known as Big Week. American bombers were sustaining horrific losses to high-altitude German interceptors. The Luftwaffe had developed new tactics, attacking from above 40,000 feet in steep dives that Allied escorts couldn't counter. Spitfire XIVs were rushed to escort duty, their crews still learning the aircraft's capabilities. What followed would demonstrate the Merlin 60 SIX's revolutionary impact on aerial warfare. Squadron leader Alex Mitchell led 12 Spitfire XIVs as high cover for B-17's attacking Regensburg. At 38,000 feet, they spotted a group of Messerschmitt 109G 6S positioning for a diving attack. In previous escorts, the Spitfires would have been helpless, watching German fighters use altitude advantage to slash through bomber formations. But Mitchell's squadron climbed to meet them, their Merlin 60Xs howling with power that seemed impossible at such heights. The German formation leader, certain no Allied fighter could reach them, realized too late that the rules had changed. The engagement that followed shattered Luftwaffe assumptions. The Spitfires not only met the Germans at 40,000 feet, but had power to spare for aggressive maneuvering. German pilots found themselves in turning fights at altitudes where their engines were gasping, while the British fighters maintained energy. 7 German fighters were destroyed without loss, several simply stalling and spinning when their pilots attempted maneuvers their engines couldn't support at that altitude. The massacre was so complete that Luftwaffe intelligence initially refused to believe the combat reports. At Derby, Stanley Hooker received a different kind of report that troubled him deeply. Engines were achieving the promised power, but destroying themselves in the process. Examination of returned units revealed metal crystallization from the extreme temperature cycling, bearing failures from the enormous loads, and supercharger blade erosion from the incredible velocities involved. They were essentially building engines that consumed themselves, trading lifespan for performance in a devil's bargain that kept Britain in the air war. The solution required revolutionary manufacturing techniques. Rolls-Royce partnered with Sheffield steel companies to develop new alloys using nickel and chromium compositions previously considered impossible to machine. They pioneered electron beam welding to join dissimilar metals without creating weak points. Supercharger impellers were carved from solid billets of aluminum using techniques borrowed from turbine manufacturing. Each innovation pushed British manufacturing capabilities to their absolute limits. German response was swift but futile. The Luftwaffe rushed development of the Focke-Wulf Tal 152H, designed specifically to fight at extreme altitudes. But matching the Spitfire XIV's performance required equally complex engineering that Germany's strained industry couldn't support. They achieved comparable altitude performance, but at the cost of low-altitude capability, creating specialized interceptors that were vulnerable everywhere except their narrow performance window. The Merlin 66, by contrast, performed well throughout the entire envelope. Maintenance crews developed unofficial modifications that pushed performance even further. By adjusting boost pressures beyond factory specifications and using 150-octane fuel acquired from American supplies, some squadrons extracted 2,200 horsepower for brief periods. These overboosted engines rarely lasted more than 20 hours, but for intercepting V-1 flying bombs or catching jet reconnaissance aircraft, the trade was acceptable. Rolls-Royce engineers were horrified by these field modifications, but couldn't argue with the results. The strategic impact became evident during raids on Berlin in March 1944. For the first time, Allied fighters could provide continuous escort from British bases to targets deep in Germany. The Luftwaffe's standard tactic of waiting until escorts turned back, then savaging unprotected bombers, no longer worked. Spitfire XIVs could maintain combat effectiveness at any altitude the Germans chose to fight. Berlin, previously protected by distance and altitude, was now within reach of British fighters. Pilot accounts from this period describe an almost surreal experience. Flight Lieutenant Robert Stanford wrote about engaging German fighters at 42,000 feet. Altitude where the sky turned deep purple and the curve of Earth was visible. Combat at these heights required new tactics. Traditional dogfighting was impossible. Aircraft moved in long, sweeping arcs, trading altitude for speed and maneuvers that covered dozens of miles. Pilots had to think in 3 dimensions across vast spaces, more like submarine warfare than traditional air combat. The engineering team faced a crisis when cobalt, essential for high-temperature alloys, became critically scarce. The entire Commonwealth supply wouldn't meet Merlin's 66 production requirements. Hooker's solution was ingenious and desperate, recovering cobalt from worn industrial cutting tools. Collection points were established at factories across Britain. Workers brought worn drill bits and cutting tools, which were melted down and refined. The cobalt from a single factory's worn tools could provide material for 3 Merlin engines. Competition with American engine development intensified. Pratt & Whitney and Allison were developing their own high-altitude engines, learning from British experience but applying American mass production techniques. The Americans offered to license-produce the Merlin 66, but Rolls-Royce refused, knowing that sharing the technology would eliminate Britain's sole advantage in high-altitude combat. This decision created diplomatic tensions but preserved British air superiority over Europe. By summer 1944, the Merlin 66 had evolved into Merlin 70 series, producing reliable power at altitudes approaching 45,000 feet. Test pilots reported phenomena never previously encountered: control surfaces freezing despite heating systems, windscreens cracking from pressure differentials, and radio communications failing from cosmic radiation interference. They were pushing into the stratosphere, territory previously explored only by balloons and experimental aircraft. The ultimate validation came on September 5, 1944, when Wing Commander Roland Beaumont intercepted and destroyed a Messerschmitt Me 262 jet fighter at 37,000 feet over Holland. The German jets had seemed unstoppable, using their speed advantage to strike and escape before Allied fighters could respond. But Beaumont, flying a specially modified Spitfire 14 with an overboosted Merlin 66, producing 2,180 horsepower, had climbed above the jet's patrol altitude. When the Me 262 pilot checked his 6 o'clock, expecting clear skies at that height, he found a Spitfire in firing position. The impossible had happened. A piston-engine fighter had bounced a jet through superior altitude performance. At Derby, the success created unexpected pressures. Stalin personally demanded Merlin 66 engines for Soviet fighters, offering unprecedented technology trades, including captured German rocket research. Churchill was tempted, but Rolls-Royce convinced him that maintaining exclusive control of high-altitude engine technology was worth more than any short-term intelligence gain. The decision would prove crucial as post-war tensions emerged, with Britain retaining air superiority technology that took other nations years to match. The human cost of extreme altitude operations became increasingly evident. Flight Lieutenant James Patterson returned from a patrol at 43,000 feet, unable to remember the entire mission. Medical examination revealed microscopic brain lesions from decompression, similar to what deep-sea divers experienced. Several pilots developed permanent neurological damage from repeated exposure to near-space conditions. The RAF instituted altitude restrictions, but operational necessities often overrode medical concerns. They were literally sacrificing pilots' long-term health for tactical advantages. German attempts to counter the Merlin 60 SIXS Superiority grew increasingly desperate. They developed methanol water injection systems that briefly boosted their engines to competitive power levels, but the system worked for only minutes before destroying the engine. Luftwaffe technical officers recovered crashed Spitfire XIVs, studying the Merlin 66 in detail, but lacked the industrial infrastructure to replicate its complexity. One captured German report described the engine as representing an industrial capability that Germany could not achieve under wartime conditions. Production statistics told the real story. By December 1944, Rolls-Royce was producing 90 Merlin 66 and 70 series engines weekly, still hand-built but with streamlined processes. Each engine consumed approximately 400 pounds of strategic materials, including metals that were desperately needed for other war production. The British government calculated that one Merlin 66 required resources equivalent to 50 standard aircraft engines. The decision to continue production represented a massive strategic gamble that high-altitude air superiority was worth the enormous cost. The engine's influence extended beyond combat. Photo reconnaissance Spitfires equipped with Merlin 70s could photograph targets from 45,000 feet, beyond the reach of any interceptor. These images revealed German jet fighter production, V-2 rocket sites, and concentration camps, intelligence that shaped Allied strategy in the war's final months. The ability to operate at extreme altitude had transformed from tactical advantage to strategic capability. Stanley Hooker's team faced their final challenge when intelligence reported German development of the Heinkel He-162 Volksjäger, a jet fighter designed for high-altitude interception. Unlike the complex Me-262, this was a simple aircraft that Germany could mass-produce. The only counter was pushing the Merlin beyond its limits. Working around the clock, they developed the Merlin 71, incorporating ceramic-coated pistons and titanium alloy connecting rods, materials that barely existed outside laboratories. The engine produced 2,240 horsepower at 40,000 feet, but lasted only 10 hours before complete failure. The war ended before the Merlin 71 saw combat, but its development revealed the absolute limits of piston engine technology. Post-war analysis showed that the Merlin 66 family had achieved thermal efficiency approaching theoretical maximums. No piston engine would ever significantly exceed its power-to-weight ratio at altitude. The team had pushed internal combustion to its physical limits, creating engines that operated at pressures and temperatures that destroyed contemporary materials, held together by engineering that bordered on alchemy. The strategic impact was undeniable. The Luftwaffe lost air superiority not through numerical inferiority or pilot quality, but through technological disadvantage at crucial altitudes. German bomber streams flying at maximum altitude were intercepted by Spitfires operating comfortably above them. Reconnaissance aircraft that had operated with impunity were hunted down. The psychological effect on German pilots, knowing that no altitude offered safety, contributed to the Luftwaffe's collapse in the war's final year. Post-war testimony from captured German engineers revealed their perspective on the Merlin 66. Dr. Anselm Franz, designer of the Jumo 004 jet engine, admitted that Germany had dismissed early intelligence about the engine as impossible. By the time they accepted its reality, they lacked resources to develop counters. He described watching Spitfire XIVs operating at altitudes where German fighters stalled as witnessing a form of engineering he hadn't believed possible with 1940s technology. The commercial impact proved equally significant. Rolls-Royce's expertise in high-altitude engine design translated directly into post-war turbine development. The same engineers who had created the Merlin 66 designed the Avon and Conway jet engines that powered Britain's aviation industry through the 1960s. The metallurgy, manufacturing techniques, and aerodynamic principles developed for extreme altitude piston engines became foundations for the jet age. Stanley Hooker's personal notes, declassified decades later, revealed the psychological toll of the program. He described nightmares about engine failures causing pilot deaths, anxiety about whether each modification would work or explode, and the constant pressure knowing that Britain's air superiority depended on his team's success. The stress caused several nervous breakdowns among his staff. They had achieved the impossible, but at tremendous personal cost. The final production Merlin 66 was completed on August 15, 1945, the day Japan surrendered. In total, 2,340 engines were built, each one essentially handcrafted, each one representing the absolute pinnacle of piston engine technology. They had taken a conventional engine design and pushed it beyond what anyone thought possible, creating power at altitudes where physics said engines shouldn't work. The cost and resources, human effort, and technical innovation was staggering, but it had given Britain air superiority when it mattered most. The legacy lived on in unexpected ways. NASA used modified Merlin engines for high-altitude research in the 1950s. Formula One racing teams studied Rolls-Royce's bearing designs for extreme load applications. Modern turbocharger technology traces direct lineage to the two-stage Supercharger design. The problem-solving approaches developed under wartime pressure became standard engineering methodology for pushing beyond apparent limitations. In his final interview before his death in 1984, Stanley Hooker reflected on what the Merlin 66 represented. It wasn't just an engine, but proof that engineering could overcome seemingly impossible challenges through systematic innovation, precise manufacturing, and willingness to operate at the edge of failure. They had turned desperation into innovation, creating an engine that shouldn't have worked but did, giving young pilots the power to fight and win at altitudes where the air was too thin to breathe but thick enough to carry victory. Thank you for joining us on this incredible journey through one of engineering's greatest triumphs. The Merlin 66 story reminds us that innovation often comes from refusing to accept limitations, from pushing beyond what theory says is possible. If stories of engineering brilliance and technological breakthrough inspire you, please subscribe and share this with fellow aviation enthusiasts. What other engineering miracles from World War II would you like us to explore? Leave your comments below. Remember, sometimes the difference between defeat and victory is measured not in courage but in horsepower at altitude. Until next time, keep discovering the innovations that changed our world.